Okay, go ahead. Go ahead.
Mm-hmm. Okay. So habitable zones, and we see these three rings, and the green one is habitable zone. When red is zone where very hot from the star, and blue one there is very cold, and liquid water cannot exist. And we see that Mars on the edge of the habitable zone, and we should ask where else can liquid water hide on Mars, and it could be under the ground or even inside snow and ice. And what we know about Mars today. So Mars is cold. It had so Mars. Mars is cold. It has thin air, and average temperature on the Mars is about minus 65 degree of centigrade, but nights can drop to minus 153 degrees. But days can go above 0 degree of Celsius in the rare spots. But we need to also talk about atmosphere of Mars, and pressure is about 0.6 kilopascal, and this is near the water triple point. So on the surface, liquid water is unstable, so it goes from the ice to vapor with this pressure. But for some conditions, there could be ice or liquid water. So stable ponds or lakes are unlikely today, and even salty brines are short-lived in open air. So we need some protection, and ice can provide that protective cover. So surface liquid is short-lived, and for life minutes are not enough. So we need longer windows, and we need a repeatable niche. So surface tricks one looked like flows, and now most are explained without liquid water. So we go below the surface, inside the slough, inside the ice, and so researchers suggest that dirty ice could be micro oases for living organism, and it is a key idea. So dust and ice can absorb sunlight, so grain warms, then it melts in a tiny pocket around itself, and it can sink and make a small cavity. So this how we see it from the surface, and this like a cross section. In this cavity, we can find life in the Mars, because we have that type of cavities in Earth's ices. So this called cryoconite holes, and they host microbes in summer. So maybe Mars can do this too. Mars also has dust. Mars has water ice, not only carbon dioxide ice on the north and south polar. And under the right sun angle, a tiny pocket could appear. So they would be below the surface. And the ice lid would block ultraviolet, and this ice would slow evaporation. So we have like a cap with liquid water where living organism can exist. And about the paper, it's paper abstract. So on Earth, solar radiation can transmit down to multiple meters within ice, dependent on its optical properties. Organism within ice can harness energy from photosynthetically active radiation while being protected for damaging ultraviolet radiation. On Mars, the lack of an effective ozone shield allows around 30% more damaging ultraviolet radiation to reach the surface in comparison with Earth. However, our radiative transfer modeling shows that despite the intense surface ultraviolet radiation, there are radioactively habitable zones within exposed mid-latitude ice on Mars, at depths ranging from a few centimeters I had a notification. However, our radioactive transfers modeling shows that despite the intense surface ultraviolet radiation, there are radioactively habitable zones within exposed mid-latitude ice on Mars, at depths ranging from a few centimeters for ice, with 0.01 to 0.1% dust, and up to a few meters within cleaner ice. Numerical models predict that dense dusty snows in Martian mid-latitudes can melt below the surface at present. Thus, if small amount of liquid water are available for these depths, mid-latitude ice exposures could represent the most easily acceptable locations to search for extant life on Mars. So what methods researchers use? First one is delta Eddington. It's SNICAR-AAD version 4. And they treat snow, firn, and glacier ice. Firn, it's a type of ice that was melted but then reappear in the next year. And they investigate different depths enough for PAR and plus safe ultraviolet. PAR, it's photosynthetically active radiation. It's about 400 to 700 nanometers. And they also use spectral optical constraint for ice and dust. And for PAR, there is two threshold. One is lower bound. It's like 10 nanomoles photon per meter square for every second, and upper bound it's 20 micromole photon for meter square for second. But for ultraviolet safety, DNA damage limit, it's around 0.1 watt per meter squared. And about model validation. So these researchers don't check exactly Mars ices. They checked Earth data, and they use Greenland bare ice measurement, and the model matches spectral measurement well, and that builds confidence. And because different wavelengths, attenual lengths behave very differently, and single lengths have huge errors. So as this figure is comparison between modeled and measured downward spectral solar irradiance in glass ice on Earth as an analog for ice on Mars. Since these types of measurement have not yet been made on Mars. And the dashed curves represent results from our solar radiation models, and the solid color curves represent measurements made in Greenland. Many existing ice models assume that no solar radiation penetrates below the top few millimeters, or use a single broadband extinction value indicated by the horizontal black line, which can lead to errors in the energy absorbed at the depths up to few order of magnitude. So these curves represent what amount of radiations goes through the surface in different wavelengths. And researchers got result, and the first result it's light versus depth. So they use clean ice, and PAR, its useful light goes deep. For clean ice, it's around 6 or 7 meters. So there is depth in centimeters, so it goes for 7 meters. And for PAR, it's around 0.4 to 0.42 micrometers. So there is its gap, whereas we see peaks. And for this depth, it's only this layer is safe, so it will be shown later. And when we have dust, it's about 0.01% of dust spectrum shift, and peak penetration moves to 0.7 micrometers, and but depth shrinks, so it's reach only around 40 centimeters for ice with grain radius around 14 millimeters. But when amount of dust increase, it's around 0.1%. PAR reach only 5.5 centimeters. So depth shrinks, and now dust block too much ultraviolet for photosynthesis. So we can make the conclusion that little dust helps, but too much hurts. So there is a so thin layer of ice for when we have dust around 0.1%. So we should consider ice with a concentration of dust around 0.01%. And so researchers get the second result, then get habitable zones, and there is figure 3. And these zones where levels of DNA damage and irradiance are safe, and there is enough photosynthetically active radiation. And photosynthesis occur are shown as the green areas. So it this one. And as a function of for pictures, first one it's dust content, second ice radius, third latitude, and fourth.
So you're in the conclusion now, right? Because we are you are in the fourth slide.
Repeat again.
Do you think that is the proper slide, right? How many slides you have? 19, right? Yeah. Okay.
It's 19,
yeah.
Yes.
Okay, go ahead.
And there is two limits of P. There is two limits for PAR shown, and it's lower limit and upper limit. And lower limit at 10 nanomoles photons per meter square for second, and upper limit 20 micromoles photons per meter per second. In biology, we scientists don't use CI unit as watt per meter squared. And so the DNA damaging limit was taken to be 0.1 watt per meter squared, and the reference value for the sensitivity analysis are ice grain radius 2.5 millimeters, density 675 kilogram per meter cubic. And dust was used as in previous slide, 0.01 dust by mass. Solar zenith angle is 0, and the latitude is 40 degree of 14 degree. And you can note that the vertical depth axis in part A is on the logarithmic scale. In part C, at each latitude, the peak solar flux over the course of the year is used. And where can we look on Mars? So the best are mid latitudes. It's around 30 to 50 degrees. So for latitudes, we can see there is the widest area. And in this area, steep slopes and impacts can expose dusty ice. Also, climate cycles deposit dusty snow during high obliquity epoch. And models predict subsurface melt in dusty snowpacks. So depth, it's around centimeters below the surface, and rate with which it melts, it's about 0.33 millimeter per day. And it can be duration about 50 solar year, sols 4 years in some cases. So it's not much water, but enough for microhabitants. And why can it persist? So inside pores, water vapor can be near saturation, and overlying dust and ice reduce diffusion to the dry air. And this slows evaporation. So water can be stable below the surface, even when the surface is harsh. And for the biology angle, about candidates for living organism, it could be cyanobacteria. Why they? So they tolerate cold, ultraviolet radiation, and low nutrients. We know that they can survive short melt season on Earth, and they can grow when water exists for only days or weeks each year. But these bacteria still need liquid water and temperature above 255 kelvins for cell division. And the modeled shallow zones can sometimes reach those conditions, but only seasonally. So thus, photosynthesis is not impossible. It is conditional and episodic. And about mission and experiment ideas, search strategy for a rover or lander. It's shallow drilling. So they should drill centimeters or tens of centimeters. They can add deeper increments about 1 meter if mass allows. Second one, in ice light probes. It measures spectral PAR and ultraviolet radiation versus depth in real data. And this validates the model directly. It could be biosign detection. We can look for pigments like chlorophyll-like, ultraviolet screening pigments, or seek microtextures, laminations, or biofilms. Also run organic and isotopic assays on dust-rich pockets. Also about thermal and humidity sensor, we can track transient melts and vapor situation in pores and correlate with light data. But we should think about planetary protection and avoid forward contamination from Earth's bacteria. And for this, we need to use sterile drills, bits, and clean protocols. But we have some limits and uncertainties, and we must be careful with claims because ice grain size at size is unknown. In the research, we use Iceland ice, not Mars one, and it changes scattering strongly, and dust contents evolves as ice sublimates. So dust can form a lac layer and then block light if it's too thick. And also geometry matters. Slope, season, and sun angle change penetration and heating. So models can overestimate or underestimate melt if inputs are off. And we still have no direct spectral lights measurement inside Martian ice. So it's a key data gap. So the papers gives a strong testable hypothesis, but we need a targeted field measurement on Mars. So also in this article, researchers use a formula for photosynthetically active radiation, PAR, and this is integral from 0.4 micrometers to 0.7 micrometers, and where both PAR that measure in volt or watt per meter square and S depends on lambda and Z, the spectral solar flux. They vary with depth. So PAR is often expressed in units of mole photons per meter squared per second, which can be converted to watt per meter squared by multiplier HCNA divided by lambda peak, where H is Planck constant, C is the speed of the light in vacuum, Na is Avogadro number, and lambda peak around lambda peak around 0.55 micrometers meters in the wavelengths of peak solar flux. So they used values of 20 micromole photons per meter squared per second and 10 nanomole photons per meter squared per second as the upper and lower limits for PAR. And this was based on observation and theory on Earth. And another formula for DNA damaging irradiance, and it's given depth given by the integral from 0.2 to 0.5 micrometers of the product of the spectral solar flux and the biological spectral weighting function for damage. And this weighting function, epsilon lambda, the use is taken from data of Cockwell and Raven, and it was derived from combination of DNA absorbance at the DNA action spectrum. It has been used successfully to represent the relative amount of damage to DNA structures from ultraviolet radiation. And following to previous studies, they use value of 0.1 watt per meter squared as the irradiance limit for DNA damage, which is a terrestrial equatorial value during vernal equinox at midday. This limits it's conservative because numerous terrestrial organisms grow and survive under stronger DNA damage conditions. Additionally, it may be possible for organisms to mutate and adapt to thrive under strong DNA damage conditions, as it is thought to have occurred in Archean Earth. So it's a reference for this article. And if you have questions, you can ask it.
Okay, let's see if there is any questions. Any question?
So I have a question. Why does a teeny amount of dust help, but too much dust hurts?
Thanks for your question. And so in the picture, we seen that dust to opposite thing. It blocks ultraviolet radiation, that is good, and it blocks PAR, and it's bad for living organism. And at very low dust, around when we have no dust at all, ultraviolet radiation drop fast, while enough PAR still gets through. And a shallow safe band appears only a few tenths of centimeter below the surface, and it's not enough. But when we have a higher dust, it's around 0.1%. We see that PR collapse to only a few centimeters, and these band shrinks or just vanished. So the main cause why we choose this dust ice, because ice warms top centimeters, and that can create liquid pockets in pores. But if dust is heavy, its heating comes to little PR.
Okay, thank you for the answer.
Write your name, please, on WhatsApp. Okay, other student who has questions?
Yes,
Go ahead.
I have.
Go
The
ahead.
question is, where exactly should we drill on Mars?
Thank you for your question. And when other researchers or robots will take examples of Martian ice, they should target exposed mid-latitude ice like 30 to 50 degrees on icy scraps or dusty snow ice slopes, because these get seasonal sun and shows ice at near the surface. And also they need to prefer equator-facing slopes for more PAR in local summer. But they also should avoid ultra clean ice that lets too much ultraviolet radiation in. So depth plan, it's around profile from 0 to 50 centimeters first, and step in 2 5 centimeters increment to cross predicted bands. But if mass allows, they could extend it to 1 meters.
Okay, if there is no more questions, then we are going to move. We are going to have the break. Okay, 10 minutes.
May I have a question?
Another question. Okay, go ahead. Go ahead.
Okay. Evgeny, thank you for your presentation. I have the question about how trustworthy are the depth ranges without real Mars data.
Thank you for your question. And so this models was validated on Earth with Greenland bare ice. but spectrum are much is good, so that builds confidence in the radiative physics. And still site parameters drive the band. It's grain size, porosity, bubbles, and dust fractions. But this paper explores ranges, and it's for different type of ice, for firn, for slow, for different type of dust contaminations, and had to PAR thresholds, so that brackets outcomes.
Okay, thank you. I get it. Thank you.
Do you have
Okay,
another
thank you very
question?
much. Well, I think that there is no more time for the. We are going to have a break for 10 minutes, and we are going to start. I don't know, depends on the next speaker. If the next speaker wants to start early, he can start early. Okay, let's see what he says in the WhatsApp. Okay, see you later.
Okay.